Yeah, so welcome back, students. So in the last lecture, we had seen the NMOS. As an inverter, we wanted the NMOS and the PMOS transistors in series, and if we want to find out the solutions graphically, the way we wanted to do graphically is to avoid the understanding of whether it is in a saturation region or linear region. So if we don't have that kind of an information with at this point of time, what we will do is we'll draw the graphical. We'll do the graphical analysis, where we will draw the profiles of the current versus the voltage profiles of the NMOS transistor, and then also try to draw the PMOS transistor's current and the output voltage profile. And wherever those current profiles are intersecting, those will be our solution points. Okay, so the VDS was nothing but the V output, and then this VDS is nothing but the VDS of the NMOS. Okay, so this particular VDS of the NMOS. And we had drawn this particular NMOS profile, assuming that the NMOS is a standalone transistor, so it is not connected to the PMOS, where one side of the NMOS, if I draw this, it is nothing but the gate which is connected with the V input voltage, and then this one is nothing but the source, this one is nothing but the drain, and the drain is connected to the output node V output, and the source is anyways connected to the ground. And that's what we have drawn the profiles of the NMOS transistor, which is the current versus the VDS profile. Similarly, if I want to draw for the PMOS transistors, right, on the gate we have, this is nothing but gate, and on this side we have the drain of the PMOS, and then on this side we have the source of the PMOS, where the source is actually connected to the VDD rail. So the source is connected to the VDD rail, and the drain is actually connected to the V out, right, from the inverter. And if I make this particular, pick those particular PMOS transistor, specific PMOS transistor in the inverter, and make it as a standalone PMOS transistor, where it is connected to the VDD rail, where the input is fed to the gate of the PMOS transistor, and this is the output node. And if I do the transfer characteristics with respect to the V input, V output, and then VDD, right, to begin with, for a standalone PMOS transistor, which is connected to the VDD and then connected to the terminals V, G, S, and D, G, S, and D. So this is what I get. So the blue lines with respect to the VDS of the PMOS, with respect to the VDS of the PMOS, this is my current profile. Right, the ISD is a positive value for the PMOS. The source to drain, this is a positive value, similar to how I get the drain to source for the NMOS is positive. The ISD is the current, which is a positive value. With respect to the VDS of the PMOS, remember that the source is always at a higher potential than that of the drain. So if I'm writing this VDS of the PMOS, that means the x-axis is actually negative. So as I go negative and negative for the VDS of the PMOS, as I go negative and negative, my current will be higher. In fact, for the PMOS, it is very replica of the NMOS. If I write the VDS of the PMOS, because VDS turns out to be negative, so it will be a mirror image of this particular red lines, which is nothing but representing the NMOS current. The blue lines represents the PMOS current. So as it is going, the VDS value is going more and more negative, it is going to start from the linear region and then go to the saturation region, right? So for a specific value of VGS of 0, right, for a specific value of VSG of 1 volts, VSG of 2 volts, VSG of 3 volts, VSG of 4 volts, and VSG of 5 volts. See, remember that I have stated it as VSG, although I have written it as VGS. So if VSG is actually 0, the VGS is also 0. What it means is if VSG is 0, if it is less than mod of VT of PMOS, which is 0.3 volts, then the current will be 0. So that's why for a VSG of 0, the current is nothing but the same line as my x-axis, right? And if the VSG is 1, that means VGS is minus 1 volts. I will get this particular profile, linear region, and then it goes to the saturation. If VGS is minus 2, that means VSG is plus 2, then I'll start with the linear region and then it proceeds to the saturation region. And similarly, for a higher values of VSG of 3, 4 and 5, that means for a negative value of VGS of -3, -4 and -5, I'll get more currents. So the more linear region and then saturation, more linear region saturation and linear region and saturation. Right, hope this is clear. So the notations, I've just slightly changed it, and you will know the reason why I have slightly changed it. If my VGS is minus 1 volts, if my VGS is minus 1 volts, right? So VGS is actually, if I can rewrite it here, VGS is nothing but V input minus VDD, which I've taken it as 5 volts. Right? So if VGS is minus 1 volts here, the input voltage, so the input voltage will be nothing but positive 4 volts. So I have rewritten this expression as V input of 4 volts. This is my current profile. Right? Similarly, if VGS is minus 2 volts, input is 3 volts. So my profile of the current is nothing but this. If input is 2 volts, that means the VGS is minus 3 or VSG is plus 3. I'll get this particular profile. And then similarly, V input of 1 represents VGS of minus 4 volts. That is what my profile will be. And V input of 0 gives me VGS of minus 5 or VSG of plus 5, which is this particular profile. Right? So what I've done is here is input side, I have the profile of the current versus the VDS for the PMOS, the current versus the VDS, for different values of VGS or VSG, I have written in the form of the input voltages. Right? Remember on this side also, I've stated the different current versus the VDS profile of the NMOS, right, in terms of the V input voltages. Right? So if somehow I bring this particular portion, this whole PMOS, right, PMOS current profile versus the VDS value into this side, right, I will get for a similar value of V input, I will get the intersection points. So that will be my solution for an inverter which is formed from the NMOS and the PMOS transistors which are in series. All right. Now notice that this VDSP here is in x-axis. VDS of NMOS, so this is VDS of N, is also in x-axis. All right. So in the next slide, VDS of PMOS, right? I'll just write it as VDS of NMOS, right, is nothing but V out minus 0. So it is V out. Okay. VDS of PMOS, if you remember the VDS of PMOS, it is nothing but the drain side, it is connected to the output, and the source side is connected to the VDD, which is 5 volts. So it is V out minus 5 volts. So if I want to bring whatever the profile I had on the negative, on the negative coordinates system. So for example, this being the second coordinate system, if I want to bring it here, right, what I have is the VDSP, which is nothing but VDS is nothing but of the PMOS is V out minus 5 volts. Right. Right. So we have drawn the profile with respect to VDS of PMOS. And if I want to shift, or rather if I want to draw that particular profile in terms of only V out, right? So this V out turns out to be nothing but 5 plus VDSP, right? And where this VDSP, V out is nothing but 5 plus VDSP. So if I can redraw the PMOS current versus the voltage profile in terms of, for the PMOS, if I can draw the current ISD versus V out, right? Currently what we have is ISD versus VDS of PMOS, but what we want is really the ISD current versus, with respect to the V out, right? So the way, we have the ISD versus the VDS of PMOS, but to draw ISD with respect to the V out profile, I need to shift the profile by 5 volts. Right, so going back to this particular slide, so whatever I have this particular profile of the PMOS, whatever I have, this is the PMOS profile. If I want to draw this particular profile in terms of V out, not in terms of VDS of P, I need to add plus 5 volts, right? I need to add plus 5 volts. So every point here, if it is 0 point here, right, to change it into V out, it will be nothing but 0 plus 5 volts. So it will be somewhere here. Right. Similarly, if it is nothing but 1 volts here, so it will get, minus 1 volts here, it will get shifted to plus 4 volts here. Right. And if it is minus 2 volts here, it will get shifted to plus 3 volts here, because I'm doing plus 5. Right. And similarly, so minus 5 volts here will get shifted to 0 volts. So the whole entire IV characteristics of the PMOS will get shifted by 5 volts, right, towards the x-axis, towards the positive x-axis. So what we have now is this blue line getting shifted, right? Earlier we had it in the second coordinate system. Now it is in the first coordinate system, because I have made the PMOS current profile with respect to the V out. All right. And if I want to do the same for the NMOS VDS of NMOS is nothing but V output. So the same x-axis is nothing but replaced by, instead of VDS of NMOS, it is now replaced by V out. Right, so for different values of V input, right, on the red line represents the NMOS characteristics, the blue line represents the PMOS characteristics, shifted, so that I'll be able to draw, I'll be able to visualize the current of PMOS and NMOS with respect to the same V output axis, right, which remains the same for both NMOS and PMOS, and the input is also the same now, V input of 5, 4, 3, 2, 1, right. So now I should be able to see both the current profiles with respect to the output node voltages for a specific input voltage on the same coordinate system. So at somewhere it will intersect. All right. So if I pick a point, let's say input of 1 volts, the PMOS is this particular blue line. NMOS input is 1 here, this one. So there is a linear region and then it goes to the saturation region. So the intersection point here for the blue line of input of 1 volts and then the red line of input of 1 volts is this particular point, the B point. Right, where the currents of the NMOS and then PMOS for the same input voltages are the same. Right, for an input voltage of 1, the current of the PMOS should be the current of the NMOS in an inverter. So that is nothing but the B point, right? So if I actually drop this B point, if I actually find out what should be the output voltage, the x-axis reflected point in the x-axis will give me the output voltage of the B point. Similarly, if the input tomorrow is 2 volts, if the input is 2 volts, the blue line input of 2 volts, the red line input of 2 volts here, it will be nothing but intersecting at C point. So the C point will give me the y-axis reflection will give me the current of the inverter, and the x-axis reflection will give me the output node voltage. Similarly, if the input is 3 volts, I'll get the intersection point as D. And then similarly for the input of 4 volts here, the intersection point will be point E. And if it is 0 volts, right, if it is 0 volts, you can see that it is actually 0 volts. The NMOS current is anyway 0. So the PMOS current should always intersect at the 0 line. So the point A is nothing but having a current of 0 line, right? And then it will have the output voltage is nothing but the VDD of 5 volts, right? And similarly, if the input is 5 volts, which is nothing but VDD value, right, we can notice that for an input of 5 volts here, red line will intersect, right, with the blue line, which is anyways, if the input is 5 volts, VGS of the PMOS is actually 0, or VSG of PMOS is actually 0 volts, which is less than the 0.3 volts, and thereby the current is nothing but this particular line, right? And so it will intersect for an input of 5 volts, it will intersect at this particular F point where the current is 0, and the output voltage is 0 volts. Right? So this becomes this forms the ABCD, starting from A, B, C, and then D, E, F will give us the intersection points or the solution points. Solution in the sense, for an inverter, what should be the current and what should be the output node voltage for different values of the input voltages that has been applied to the inverter. Right? So to be very, very specific with respect to the points A, B, C, D, F, right? I've drawn a table here. So the profile is nothing but the same. The input, NMOS current profile with respect to the Vout, PMOS current profile with respect to the Vout for different values of input voltages. The intersection points give me A, B, C, D, E, F, right? So these points, intersection points, have written down A, B, C, D, E, F, right? For an input voltage of 0, I'll get the intersection point as A. For an input voltage of 5 volts, I'll get an intersection point of F. For an input voltage of 1, 2, 3, 4, I'll get the intersection points as B, C, D, E respectively. Right. The output voltage also have drawn it, I also have written it, although I don't know the exact value. What I've stated is the intersection point B, so this particular point B, it's actually very, very close to the VDD of 5 volts. So that's what I've stated here, close to the 5 volts. Point C is actually very, very close to, again, it is this particular point, again, very, very close to 5 volts and not to 0 volts. So it is close to the 5 volts. So that's what I've stated here. Point D here is actually close to 0 volts and not to the 5 volts. So that's what I have stated here, close to 0 volts. And point E is also close to 0 volts. Let's try to find what is the current, right? So the current of A and current of F is anyway 0. So that's what I have stated here. Current of A and current of F is 0. Current of B. So the current of B here. So this is my intersection point, right? For the NMOS side, it is the saturation current. For the NMOS side, it is nothing but the saturation current, which is intersecting with, this particular blue line, right? This particular blue line, although I've now made it, black, but this particular blue line, the earlier blue line was nothing but the linear region. So at point B, it was actually the PMOS was in linear region, NMOS was in saturation, right? So if I want to find out what is that particular current, I can actually go with the equation of the ID saturation of NMOS, find out, the point B, right? So point B, the ID saturation of the NMOS, and find out that particular current value. It is nothing but the ID saturation current of NMOS equated with that of the the IDS of the linear of PMOS, the linear current of the PMOS, right? Point C is also the same. We have the NMOS saturation current equated with that of the linear current of the PMOS. I'll get the point C. Similarly, D is nothing but the PMOS saturation current, here equated with that of the linear region. D is nothing but V input of 3 here. So V input of 3. So this is my, the linear region of the NMOS and then the saturation region of the PMOS. E is also the same. PMOS saturation region equated with that of the linear region of the PMOS. The saturation region of the PMOS equated with that of the linear region of the NMOS. And then point F is nothing but 0. So if I look into this B and C, it is nothing but saturation region of the NMOS equated to that of the linear region of the PMOS for a particular value of the input voltage. Right, point D and E, point D and E is nothing but the saturation region of the PMOS equated with that of the linear region of the NMOS for a particular value of the input voltage will give us those points. Right, so hope this is clear. Right, so remember, in most of our applications, we will always have the input voltage at A or F. In fact, input voltage at 0 or 5 points. So my solution points are always A and F. So the current, if you look into the current for the points A and F, it is always 0. Right? So in a steady state, operation of an inverter, steady state implies that once the input is given and after a certain time is over, after the transition is over, the output voltage will be either 5 volts, or 0 volts in a steady state voltage, and then the steady state current is actually 0 in both the cases, right? Now that is a very significant point or an advantage or a benefit for the CMOS transistors. So the CMOS based circuits, whether it is an inverter or a NAND gate or a NOR gate or any such combinational circuits, ideally the current is 0 in a steady state, and hence this particular topology or this particular CMOS, where the CMOS circuits or the compound or the combinational circuits are placed within the VDD and zero rail, VDD and ground rails. So those particular topologies, we call it as the static CMOS circuit families, right? And then the reason for this being called as a static is, in a steady state, the current is actually 0, right? So ideally, the current should be 0. We will look into the leakage currents later on, where we will see that, even though it is a static CMOS or even in a steady state, there will be some current that is being leaking, right? But apart from the leakage current, right, there is no current that will be flowing. If I draw the inverter here, the VDD here, connected. So this is my inverter, right? So there is no direct current which will be flowing from VDD to ground in a steady state, right? Of course, there will be some kind of a current which will be flowing to the to raise this output node from 0 to 5 volts or 5 to 0 volts, and then from current flowing to the ground. But once it reaches the steady state value, after that there won't be any direct current from VDD to ground, right? And thereby this particular 0 current, and that's why it is called as a static CMOS circuit families. And that is one of the significant advantage of this the CMOS static CMOS circuit families, is the current dissipation from VDD to ground is 0. And if the current is actually 0, right, current multiplied by VDD, the VDD is nothing but the voltage, the potential difference between this particular rail and this particular ground rail, is also 0. So the power dissipation is actually 0 in a steady state for a static CMOS circuit families, right? So that is one of the significant advantage. Moving ahead, if I want to draw, now that we have this particular intersection points, A, B, C, D, E, F, and then it's the current value, its input voltage, is output voltage. Although we don't know the real output voltage, graphically we can only say that it is close to 5 volts, close to 5 volts, or close to 0 volts or 0 volts. The current values, we know some particular, we can write an expression. But putting those points of A, B, C, and then D, E, F, and drawing the profile of V output with respect to idea. So it is basically capturing those particular values from the graphs, from this particular point where we had this intersection points, right? We should be able to draw the current here versus the output voltage. So I've taken out all other things. I've taken out the NMOS profile, current profile, PMOS current profile for different input voltages, and only pick those points, right? A point, B point, C point, D point, E point, and F point, and have drawn this particular, I've connected these points. There is one additional input here where I've taken a point of input of 2.5 volts, right? So 2.5 volts actually lies between VDD of 5 volts and ground rail of 0 volts. And it becomes a very significant point here because, right, this particular point intersects, this particular solution of input of 2.5 volts. Now, if I want to find out what is the current, I need to actually equate the saturation current of the NMOS and then the PMOS, right? So graphically, you can see that for a 2.5 volts of input, right, the saturation profiles of the NMOS and PMOS are going to intersect, right? So, and then if the saturation current intersect, I'll get this particular point. Interestingly, if the betas are same, if the betas of PMOS and NMOS are same, which in our case we have taken to simplify these things, this will be nothing but 5 volts divided by 2, so nothing but 2.5 volts, right? In fact, now Now for this particular point, 2.5 volts, in fact, I'll get a series of points. So the saturation profile of the NMOS, the saturation profile, let me use a different ink. So the saturation profile of the PMOS. So this will be the PMOS, the saturation profile of the, let me draw the different one. So saturation profile of this particular value is something like this. So I'll get actually a series of points. So I'll use a blue ink. For a 2.5 volts of an input, I'll actually get a series of points around this 2.5 volts. So that is, if I'm changing the input voltage from 0 volts to 1 volts to 2 volts to 2.5 volts to 3 volts and then so on, I'll get the series of saturation points or the transition region where the output voltage goes from 5 volts to 0 volts. Okay, so that is something we will see now. And then this is again another profile of IDS with respect to input voltage. So the earlier one was IDS with respect to output voltage. So I've drawn with respect to the input voltages those series of points A, B, C, and then D, E, F. And then this is one point, G point, where the input is 2.5 volts and where I will have the NMOS and PMOS saturation current to be equated, right? And then this is the last one is the transfer characteristics where we have the output voltage drawn with respect to the input voltage. So I now have the points A, B, C, D, E, F, and then this particular G point. So notice that the G point, I will actually get, this particular, I should start from here. So G value, in fact, this turns out to be a line. This turns out to be a straighter line. So for an input of 2.5 volts, I will actually get a series of solution points, all right, around the G value. The G value turns out to be close to the 2.5 volts, right? So this transfer characteristics is one of the important characteristics for an inverter. We can always draw the transfer characteristics for a 2-input NAND gate or an OR gate or any number of inputs of the universal gates or any other combinational circuits. But this particular transfer characteristic states that if I apply an input of 0 for an inverter, I'll get the output of A here. Right, if I apply an input of 1 volts, I'll still get the output close to the, this one is 5 volts. So close to 5 volts. If I apply an input of 2 volts, I'll get the output close to 5 volts. If I apply an input of, 5 volts here, the output is 0 volts. If I apply an input of 4 volts, I'll get output close to 0 volts. And if I apply an input of 3 volts, I'll get an output close to 0 volts. Right, so this is how the transfer characteristics of the inverter looks like. And it states the working of the inverter, right? It clearly represents the working of the inverter.